Hello again, everyone, and hello to those watching in the future. This is a revision seminar for Maths 1B in Semester 1 of 2021. I'm David, I'm the coordinator of the Maths Learning Centre, and I've had a request to talk about some of the multivariable calculus stuff in Maths 1B. The rules are, those of you who are here live, feel free to interrupt me if I make a mistake, if I lose a minus sign or add a minus sign or do something like 1 + 1 = 1. Please let me know immediately. It's okay to interrupt. Don't wait 5 minutes and tell me I've made a mistake. Otherwise, feel free to wait till I've finished a sentence and then let me know any questions that you've got. It's always okay to ask questions. I will keep an eye on the chat, and I'll try and stop every 5 to 10 minutes and check in with you. So please make sure that you have questions and be ready with them if you've got them. Those of you watching online in the future, well, you can't really interrupt me, but if you're a University of Adelaide student, then feel free to drop into the Maths Learning Centre and have a chat about any of your questions. Okay, I've been asked to talk about some multivariable calculus things. If I'd known in advance I was going to do this, I would have brought some things, but I'm going to run with it as I am. I'll deal with it. So I'm just going to talk for a bit and then see how you feel. When you did one variable calculus, you were used to seeing some sort of function and being able to figure out a derivative or an integral of that sort of thing. And that was ordinary calculus. And the idea is that the x is one variable and the y is another variable, but it doesn't, when we talk about one variable calculus, we're not talking about the output, we're just talking about the input. Okay, so we know that if we were at a particular spot and we moved one way or the other, then the function value will go up or down, and it will change if you move a little bit. And that's what calculus of derivatives is all about. If you move a little bit, then how much does the function change? And it turns out that if you're extremely close to the function, then it works the way a straight line works. So if I have a magnifying glass here and I zoom right into my function, then it's nearly straight at this spot. And so if I move a little bit this way, then the function will go up a little bit that way. And if I move a little bit this way, the function will go down a little bit that way. And this is an increasing function, and some functions go down like that. Okay, and we learned that, that if you're at one of these positions, where when you zoom in, it's almost flat, then that's when the function is at its lowest or its highest. Okay, so I just want to change to a different perspective of how this works. This drawing here is a picture of what the function value is doing. But you can imagine that there is just a line of x's, and every x has a number attached to it, which is the outcome for the function. So if I had the function value f of x = x squared, and I went like this, then at this point, the function value is 0. And at this point, when I sub it into the function, I get 1. And this point, I get 4. And this one, I get 9. And this one, I get 16. I also get 1 here. And then at like 1.5, I'll get 2.25. And every point has a number attached to it. And what I can try and do when I do calculus is to say, well, if I move along this line, how is the number changing as I move along this line? And that's what this graph is saying, where we interpret this number as a height. And we say, how is the height of the graph changing when I move along? But the reason I want to talk about this is that there's nothing stopping me doing this for a plane as much as I do it for a line. I could say that here's an x and a y, and at every point here in the plane, I'm going to attach a number. So maybe here I'll attach 1, and here I'll attach 2, and here I'll attach 2 as well. And maybe here it'll be a 3, and here it'll be a 7, and here it'll be an 8. And every point has a number attached to it. And I can imagine if I'm at a particular spot, and I move in a particular direction, if I'm at this spot, maybe the answer for my random made-up function that I'm making up is maybe 10. And if I move this way, maybe it'll go up to 11. And if I move, say, this way, maybe it'll go down to 9. And different directions, the function values will be different. So that's the idea of a multivariable function, is that at every position in either a plane or in 3D or on a line, well, that's a single variable function, but every position, there is a number attached to it. And as I move around, that number changes. And what I want to know is if I move in different directions, where is it going to go up or down, and how fast is it going to do that? And normally we would interpret these numbers as heights. So here where it's 2, I'd go up just a little bit. Here where it's 7, I'll go up this much. Here where it's 10, I'll go up even more. And you interpret it as a height, and what that produces is a surface, something that's some sort of shape. Just a second. A surface that's sitting above the XY plane or below it, because the answers are allowed to be negative. So you tend to interpret it that way, but you don't have to. You can just imagine that there is a number attached to every point. And the reason I say this is because I can't do this in 3D. Yes, two variable functions create surfaces. If you interpret the outcome of the function as a height, and draw a dot for every one of those, that will make a surface. That was a great question. In 3D, it's a little harder to do that, because I might have an X and a Y and a Z, and there'll be a number attached at every point. In 3D space, and the answer is what this number is, and there's no other dimension to draw that height in. And so I can't think of this as X and Y produce a height, or X produces a height. I can't do X, Y, Z produces a height, because there is no place to draw that height. So it's just easier for me to think of it as a number at every point. So for example, what people use this sort of thing for is the strength of the electrical field, for example, or the temperature. At every point in this room, there is a temperature. And you can even do this where every position and every time together produces a number as well. So, yeah, that's the first thing about what's going on. And one of the major things we want to do is, if we're at a particular spot and we move in a particular direction, we want to know how quickly the number is changing. All right. Cool. So ultimately what we want is what you eventually got called the directional derivative. This is the ultimate goal of what we're trying to achieve here, and it can help us to do a lot of things. So if I have a function that takes both, X and Y and Z and produces an answer, usually there's a formula in this spot here. So this is what you'd normally see. So for example, you'd see something like that. And what this is saying, that if you pick a point in 3D space and sub it in, it'll give you an answer. And every point has an answer. So what I want to know is, if I'm at a particular point, say I'm at the point 1, 1, 2, and here's 1, 1, 2, 1 for the X, 1 for the Y, and 2 for the Z. If I'm at that point, there is a function value. Which in my case is -1. And the question is, if I'm here and the number attached to this is -1, if I move in various different directions, will that answer go up or down? Will it go towards 0 and become like -1.8? Sorry, will it go -0.8? Will it get even more negative? What will happen? And it should be different in different directions. And that's the directional derivative. That's what we'd like to know. Yep.
Function of x1, one variable creates a line and then xy the circles, and xyz what is?
There is nowhere to draw that.
It's just 3D.
Well, it's like in this one, the domain, the x and y, that's 2D. And then the answer is a third dimension, which creates a 3D space where you draw the surface. And in this one, the input is one dimensional and the answer is another dimension, which would create a plane where you would draw a line. In this one, the input is three dimensional and the answer would be a fourth dimension, and there is nowhere to draw that. Yeah. That's the problem. And that's why I like this imagining of it. So I imagine being like a fly flying around the room and say, I'm a particular spot. How much is the number changing as I move? How much does it feel hotter or colder? Yeah. So if we move that past this in different directions, does the value of the number go up or down? And how quickly? That's the question we want to know. And the answer to this question is the directional derivative. I'm just going to look up in the notes and check a notation, and I'll be with you again in just a moment. Okay, cool. Okay, so I'm going to do it in 2D first with a new function because it's a little easier to think about. It's just a random function I'm thinking off the top of my head. Okay, and here I am in 2D. There's my x and my xy, and every point has a number attached to it. So I could, if I wanted to, calculate these points, and I will do it for a few of them. So when x, plus 1. So when x is 0, I get, when x and y are both 0 at this point, I get 0 times 0 minus 0 squared plus 3 times 0 plus 1, and the answer here is 1. And here at the point 0, 1, 0 times 1 minus 0 squared plus 3 times 1 plus 1, the answer is 4. And here at the point, sorry, damn it, that's the point 1, 0. 1, 0, 1 times 0 minus 1 squared plus 0 times 3 times 0 plus 1, the answer is 0. Whereas at 0, 1, 0 times 1 minus 0 squared plus 3 times 1 plus 1, the answer is 4. And here at 1, 1, the answer is 1 times 1 minus 1 squared plus 3 times 1. The answer is also 4 there. And here at 1 minus 1, I get minus 1 minus another 1, which is minus 2, times 3 times minus 1 plus 3 times minus 1. So now we're at minus 5, so it's minus 4. And every point has a number that's attached to it. Good-o. So I'm going to start at this point here. It's a coincidence that the answer is 0 at that spot, but I just want to start there. So f of the point 1, 0 is 0. Okay, my question is, I'm just going to figure out this point 2. 2, 0, minus 4. My question is, if I'm at this point and I move away from this point, is the answer going to go up or down? It seems to me if I go this way, the answer is going to go down, because I'm going to go from 0 to minus 3. If I go this way, the answer is going to go up. If I go this way, the answer is going to go up, but faster than this way. If I go this way, the answer is going to go down, but slightly faster than it goes down here. And if I go diagonally, I don't know. It might be difficult to tell. So what I would like to know is that, and that's called the directional derivative. So if I'm going to draw this diagonal line here, there. That vector is the vector 1, 1. So the directional derivative in the direction of the point 1, 1 of the function f at the point 1, 0 is a number. And that number is the speed at which the answer is changing when I move in that direction. So this is what it is. This is what I imagine it to be. That's what's in my head. This is the speed that the function value is changing when I move in the direction of 1, 1 past this point 1, 0. But the actual terminology is that this stands for the directional derivative. And this is in the direction of the vector 1, 1. And this is of the function f. And this is at the point 1, 0. And so each piece of this is read aloud in a different way. So I don't know what that's going to be. But I do have a guess that the directional derivative of f in the direction of, at the point 1, 0, in the direction of 1, 0, so that way, looks like it's going to come out to be negative. And this way looks like it's going to come out to be positive. And it turns out that what you need to do to figure out what this directional derivative is figure it out in the two x and y directions first. Okay, so just a second, I'm going to say this directional derivative, the directional derivative in the direction of 1, 1 of f at the point 1, 0 will be this speed. That if I head past this in that direction, that's the direction of 1, 0, how quickly is the function value changing there? And if I head past this in this direction, how quickly is the function value changing there? That would be useful to know as well. And it turns out that this, watch very closely, if I go this way, then I'm changing the value of x, but the value of y is staying the same as it was before, if I go this way. And if I go this way, I'm changing the value of y, but the value of x is staying the same as it was before. And so this is called the partial derivative with respect to x at the point 1, 0. I really shouldn't have used 1, 0 there. That was a bit of a bad plan. And it's probably a bad plan for me to do this at all, but you know, I'm just pointing things out that I really want to know how these things change, and it's really easy to do this one. So let me come back a bit and change direction. Yep. This one, not the other one. It's bad to use this number as my example. I mean, I can use this number there, but I really want it to be at a random point. So anyway. Yeah, they're the same one. So I need to do a new example. I'm sorry. This is what happens when you make it up on the spot. I've got a question. It's D11 and not D10. Yeah, I'm just going to start again. So, the point I was trying to make, and I'll come back to this in a minute, the point I was trying to make is that it might be difficult to figure out the directional derivative in just some random direction, but it's going to be actually easier to figure out in these two directions that follow along the x and the y axis. So I'm just going to start again. I'm going to go to the point 2, 3 instead.
Can you just pick the random point?
Yeah, I'm just picking a random point for my example. just so it's easier for me to see what's going on. So if I've got a random point and I'm thinking about moving past it in the direction of the x-axis or moving past it in the direction of the y-axis, those two directional derivatives have names and they're easier to calculate than any of the others, because the directional derivative at the point in the direction of 1, 0, at the point of the function f at the point 2, 3, is the speed at which the function value changes going past the point 1, 2, 2, 3, because that's the point we're at, in the direction of 1, 0. That's what this is the same as, I'm going to think of this, keep the y value the same because I'm going this way, so that's always going to stay at height 2. And how quickly does f change when x does? That's what I'm asking if I'm going in this green direction here. So this 1, 0 is this green direction here. The derivative is the speed at which the function value is changing. And if I was up here on the surface, I could slice my surface here. I could slice my surface here and draw a line and go, oh, it's going downwards here. And so that would be a negative number. So, just a second, there's a name for this thing. This thing here is called the partial derivative with respect to x. It's called partial because I'm picking one part of the way the function moves. I'm picking the x and not the y. And I'm keeping the y the same, and I'm only moving the x. And there's a notation for this. This is the derivative of f with respect to x at the point 2, 3. The way to do it is to literally differentiate your function as if y was a constant. So let me figure it out. So my function was x minus x squared plus 3y plus 1, just a random function I was thinking of. And then df on dx, I differentiate this pretending that y is a constant. Because the idea of the df on the curly df on curly dx, so these are not straight, these are not this d, it's this d. And I believe what most people read aloud as curly d, but you can say partial d. This thing is how quickly this moves when the x changes but the y doesn't. And so I treat the y as a constant. And so the derivative of a constant times x would be just the constant itself. And the derivative of 2x would be 2x. And this is a constant. And so it would disappear when I do the derivative. It would become 0. And this is a constant too, and so I get this. And so the derivative with respect, partial derivative with respect to x at the point 2, 3 would be y is 3 and the x is 2 and it's negative 1. So this is saying that if I move in the direction of 1, 0, a teeny tiny bit, I move this way a little tiny bit as I'm going past this point, then the function is going down at a slope of negative 1. There would be one here is 2, df on dy. At this time I would treat x as a constant. I have constant times y, so the derivative would be the constant. That doesn't involve a y, so it counts as a constant, so it'll disappear entirely. The derivative of 3y would be just 3. And so df on dy at the point 2, 3 would be x plus 3, which is 5.
And is this slope? So -1 and
They are slopes. But they are not slopes on this diagram. They are slopes on this diagram where the surface is. So it says that if I go this, what is the height at this point? Just let me figure that out just a second. So out of interest, I'm just going to figure out what f of 2, 3 is. F of 2, 3 is 2 times 3 minus 2 squared plus 3 times 3 plus 1. So 6 minus 4 plus 9 plus 1, which is 12. Okay, so the height here is 12, like all the way up here, there. And it's saying if I go this way, then it's going down. Whereas if I go this way, then it's going up at a speed of 5. Damn it. There's my 12. If I go in the direction of the y, it'll go up at the speed of 5. If I go in the direction of the x, it'll go down at a speed of 1. That's what that's doing there. Yeah?
So it's just, so when going in that back to the direction that you're going, so 1, 1, would that mean that it would form similar to like a plane going along that?
Exactly. And that is exactly what it's doing. So I know, I need something that, I'm going to pretend this is of height 12. Look at it from over here. Sorry? So, yeah, if I go this way, it'll go down 1. If I go this way, it'll go up 5. And that would be something of this flavor. And you're imagining there's a plane filling that in? Yes. I mean, it only does this when it's extremely close to this point, because the surface itself is curved. But when you're very close to something that's curved, it will feel flat. And so that plane there is what it looks like. So if I want to go in the direction 1, 1, I should follow that plane. That's called the tangent plane at this point, the plane that we're thinking of just there. So you have just discovered the directional derivative, like how to calculate it. So the way to calculate a directional derivative is that you combine the two partial derivatives together with the direction that you're going. So if I want the directional derivative in the direction of 1, 1 of the function f at the point 2, 3, then what I'm going to need to do is combine these two slopes that I've calculated together in some way based on that plane. And so I need to figure out how much I'm going in the x direction and how much I'm going in the y direction. And it's the same for both for this one. And so it'll literally be -3 times something, because what I want to make sure, I'm just going to draw something. This is where I am. If I'm going the direction 1, 1, that's this. And the direction 1, 0 is this. And this vector is longer than this vector. That's not going to work, because even with an ordinary function, if I go a further distance, the function will go up a further amount or down a further amount. So I need to make sure that the direction that I'm going is the same distance as these directions as well. So I need to make this into a unit vector in order to use my thing. So first, to find this, first I find df on dx at 2, 3, and that was -1, and df on dy at 2, 3, and that was 5. I also need to find a unit vector for the direction that I'm going. So I need to divide this vector by its length. So first, to make a unit vector out of a vector you've already got, you need to find the length of your vector, which is 1 squared plus 1 squared, which is √2. And then to make a unit vector, I should divide the vector I've got by the length. So that's a unit vector. And then I need to have this amount, the x coordinate amount of this value and the y coordinate amount of this value, which is the same as doing a dot product. So now the answer is the unit vector dot with the vector made of the two derivatives. Minus 1. Here? This is df on dx, the partial derivative with respect to x. And this is df on dy, the partial derivative with respect to y, which I just figured out came out to these answers at this spot. Oh, no, this is the first thing to do, and then this is the second thing to do. Sorry. Second thing to do is this, and then the third thing is the actual answer. Sorry, it was a process.
So we found, so in the direction of 1, 1, we found 1, 0, but we find 0, 1, or?
Yep, so this was the 1, 0 direction.
Yeah.
This was the 0, 1 direction.
Oh, okay.
Because that's pointing directly up. So going in the 0, 1 direction is the same as doing df on dy. Yeah, pointing directly up the y-axis, parallel up the y to the up y-axis.
And then 1, 1 is a combination.
And then 1, 1 is a combination of those two answers based on a unit vector in the direction that you're going. Cool. So let me just run through that again. Given any function whatsoever that I know how to calculate derivatives of, I can find df on dx and df on dy, like the partial derivatives, and they represent directional derivatives in the direction of x and in the direction of y. And in order to create a directional derivative in any direction, I need to do a unit vector in the direction I'm thinking of. I need to find the partial derivatives, and I need to create a dot product. And that's what it is. So this is 4 on root 2, which is the same as 2 root 2. So approximately 2.8. So this is saying that if I go in the direction of 1, 1, go past the point 2, 3 in the direction 1, 1, that way, then the speed at which the function value is increasing is 2.8 per unit across. So if I go across 1, I'd expect to go up 2.8. Sorry? Create the unit vector.
So are we normalizing?
Yep. Normalizing is the process of turning an ordinary vector into a unit vector. Good use of terminology there. It's also always important to line up the words to it so we know what they mean. So that's finding a directional derivative. Cool. So there's one piece of here that I haven't mentioned a terminology that goes with it. This thing is called the gradient of f at the point 2, 3. The vector which has the two partial derivatives is called the gradient. Whew, okay. So some people call the gradient the derivative of f. And it is, in many contexts, that. But the thing we really want to know is the directional derivative. We want to know if I change a little bit in one direction and another simultaneously, how much would the answer change? But the gradient allows you to calculate any of those directional derivatives. And so it's a really useful piece of information. But the gradient doesn't just tell you that information, and there's some extra magic tricks that happen that allows you to say some other things. The magic of the gradient is that if I go in this direction, that's the direction to go to make the function value change the fastest. So it's not just a handy vector in which to hold the partial derivatives. it's also a direction that you can go. So I'm just going to say that properly. So let me just summarize where we've got. We have a function. And we can do the partial derivative. With respect to x. And that means that you hold y as a constant and do the derivatives the way you expect it to. And we have df on dy. That's the partial derivative with respect to y, which means we hold x constant. And those two are already a kind of directional derivative. They are the directional derivative in the direction of 1, 0, and the directional derivative in the direction of 0, 1. And then there's the gradient of f, which is a vector that contains df on dx in the first coordinate and df on dy in the second coordinate. This is what they're called. That's why I put the inverted commas there. And then the directional derivative of, in the direction of u of the function f at the point xy is the unit vector dot with the gradient of f at this point. But this has to be a unit vector. This doesn't have to be, but you have to turn it into a unit vector in order to use this formula. So in a technical sense, it's u divided by the length of u that goes in this spot. Okay, and this is the of f at xy in the direction of u. You can say those in whatever order you want. It probably is okay to say directional derivative in the direction of u of f at xy, but it doesn't matter which piece of these of f at xy in the direction of u. You can say them in any order. You can say the directional derivative at xy of f in the direction of u, and that'll be fine too. Okay, and just as a final note, df on dx is the same as the directional derivative in the direction of 1, 0 of f. And df on dy is the same as the directional derivative in the direction of 0, 1 of f. Okay. Sweet. This works perfectly well in 3D. The only difference will be that there will be a df on dz as well. Everything else will be the same. And this won't be 1, 0, it'll be 1, 0, 0. And this won't be 0, 1, it'll be 0, 1, 0. And the df on dz will be d 0, 0, 1. Cool. Sweet. So what do we do with this information? We can figure out the directional derivative, which means we have an idea of whether it's going up or down in different directions. There are some other useful things that we can do. We can also know that the gradient of f is not just a handy place to hold the derivatives, it is also a direction to go once you've figured out what it is with its actual coordinates. And if you go in the direction of the gradient of f, then the directional derivative is the maximum. And if you go in the opposite direction to delta f, then the directional derivative will be the maximum but negative. It is also the minimum, but it just is a bit confusing to say minimum change because that would make you think 0. So it is the maximum slope in that direction. If you go in the opposite direction, it's the minimum slope, meaning the biggest negative slope. Yeah.
So is that a saddle point?
No, I'm not up to that yet. Okay. Okay. So for example, my original function that the one that I was thinking of before, at the point 2,3, I know that the gradient at this point I already figured out. The gradient of f at the point 2,3 is the vector minus 1, 5. If I go in the direction of minus 1, 5, minus 1 for x and 5 for y. Damn it. Minus 1 for x and 5 for y. That direction. That's the direction I should go to make the function value increase the fastest. So the function value at this point was 12. If I go that way, it'll go up from 12 the fastest it can possibly go. If I went any other direction, then all of these directions this way, it would be going up. And all of these directions this way, it would be going down. And these directions sideways, it won't be moving at all. I mean, if you go far enough, it'll start changing. But if you just go a little bit, it won't change much at all from 12 if you go sideways. So it'll be going up these ways, and it'll be going up really fast, and then not so fast and not so fast, and it won't change at all this way. And down this way, it'll be going down faster and faster, and down really fast in this direction, and so on. So the maximum slope is in the direction of minus 1, 5. And are you ready? This is the real magic trick. The actual slope in that direction will be the length of this vector. So the directional derivative of the function f in the direction of minus 1, 5 at the point 2, 3 will be the unit vector of this, the unit vector in the same direction of this, dot with the gradient, which is this, and that will produce the same answer as the length of that vector, which is a magic trick. So it will be just the length of this vector. What, 5.1-ish? I don't know. That's what calculators are for. I was right. To one decimal place, 5.099. So I think I did pretty well. Let's just be more precise. So this is the fastest you could possibly make this go if you go past the point 2,3. So if I come past the point 2,3 in that direction, it'll be going, every one across will be a little bit more than 5 up. If I come down, if I go this way, it'll go down. How are people feeling about what's happening here?
Where did you get f equals 12 from?
Oh, I subbed it in. F equals 12. I did that back here. I subbed in 2, 3. Yeah, that's why I keep talking about the number 12. So that's the height at this spot. So the minus 1, 5, the minus 1, 5 is about the slope. It doesn't actually have almost anything to do with the height at this spot. And I used the 2 and the 3 to figure out what these numbers were. But I also can use the 2 and the 3 to figure out what this number works out to be. And this is how quickly that number changes as I move past this spot in that direction. Okay. So if you want to know what U is, what will happen is that someone will tell you which direction you're interested in. So they'll always begin by telling you, I want the derivative in the direction of 1, 1, or I want the derivative in the direction of 5, 7, or I want the derivative in the direction of minus 1, 3. They'll always tell you the direction. If you're told the direction, just a random number at a particular point, then you need to figure out the gradient and you need to figure out a unit vector in this direction. So my unit vector is going to be this vector divided by its length. And that vector is, well, the square root of 5 squared plus 8 squared, which is, a terrible number. I don't know what that is. 64 plus 25 would be 89. So that's to figure out what u is, and then that answer here goes there. And then you figure out the gradient by doing df on dx and df on dy. However, yeah, and so when you're finding df on dx, that's exactly the same as finding this. But it's much easier to find this by just doing the derivative and ignoring the y and treating it as a constant. So I could do all this process, but I don't have to worry about that. And this is already a unit vector. And so I don't have to do any calculations. I don't even need to do this calculation at all. I know it's there. This is what I imagine it to be, but I'm going to do this with y as a constant. But this is what the u is in that context, in this context. But I don't have to find the u because I don't do this at all. I just do derivative with y constant. And it comes out to the correct answer anyway. Cool. There's one final situation. If someone asks you, what's the correct direction to go to make the derivative the fastest, then you have to choose the direction. And the correct direction to choose is the gradient. So that's the only situation in which they would ask you for a direction to begin with, is to say which direction is the fastest, or which direction has the fastest decrease, which would be the opposite direction. So this is the maximum slope. It's also the direction. The maximum slope is in that direction. The maximum speed of increase is in that direction. The maximum speed of decrease would be in the direction of 1 minus 5. Okay. We're doing very well. So most functions, you're interested in where the maximums and minimums are. And back when you did ordinary derivatives, for one variable functions, the maximums and the minimums happened when the derivative was 0. And that will happen in two variable functions as well. But what you need is both derivatives to be 0. In fact, you need all the derivatives in every direction to be 0 simultaneously. So to be a maximum, you need all the directional derivatives to be 0 in every direction. But the cool thing is that if you make df on dx 0 and df on dy 0, because of the dot product, that'll make it come out to 0 in every direction anyway. So what we really need, we need the gradient of f to be the 0 vector, which means we need all the partial derivatives to be 0. So that's the long version. Short version is, in one variable calculus, you need the derivative to be 0. In two variable calculus, you need both the partial derivatives to be 0. In three variable calculus, you need all three of the partial derivatives to be 0. And you need them to all be 0 all at the same time.
Is that like the null space for grading all that?
Yeah, so if you're going to connect it to algebra, this is indeed the null space, but null space goes with matrices.
Is it grading f a vector?
It is, yes. But
Equal to...
yes. So you're actually making connections that are extremely important. but we don't call it the null space in this context because the gradient was produced by differentiation, not by matrix multiplication. So when you do null spaces, it's matrix times vector equals 0, and you call that the null space of the matrix. But you've done derivative equals 0. Derivative produces vector, which is 0. And so it's a bit tricky to talk about a null space in that context because there's no matrix there.
So if the gradient of f, for example, in our...
Yeah, let's do it. Yes, yes, yes. So our function was xy minus x squared plus 3y plus 1, and df on dx turned out to be y minus 2x, and df on dy turned out to be x plus 3. Is that right? Is that what they came out to last time? Yeah, okay. Then our critical points, they're called. I don't know how many there's going to be. The critical points happen when both derivatives are 0. They need df on dx to be 0 and df on dy to be 0 as well, which means I need y minus 2x has to be 0 and x plus 3 has to be 0. And I need both of those to be true at the same time. If you're very lucky, like we are today, one of them will only involve one variable, and you'll be able to figure out what numbers go with that. This would be x equals minus 3. And then I'm going to sub that into number 1. Damn it. There's number 1. Sub that into number 1, and I'll get y minus 2 times minus 3 is 0. And so y plus 6 is 0. So y is minus 6. So I get one critical point. Which happens minus 3 minus 6. So this is a location on my graph. I'm told that we know that earlier that the derivative at 2, 3 was equal to, well, you know, minus 1 in the x direction and 5 in the y direction. If I go to minus 3 minus 6 here, the derivative there is 0 in both directions, and therefore 0 in every direction. So I've got a really good chance of that being the top of a hill or the bottom of a valley. But in 3D, we can get other things happening, like on my knuckles here. That's the bottom of a valley this way, but it's the top of a hill that way. That's a saddle point. And so that point there, the directional derivative is 0 in every direction as well, but it's not a maximum and it's not a minimum. And that's called a saddle point. So, well, that happens in one variable calculus as well. It's a maximum from the left-hand side, but it's a minimum from the right-hand side, which is what you get an inflection point in that case. But this is worse. Yeah. So I need to know, is it one of these, or is it one of these, or is it one of these, which is a little valley in my hand there. So is it the bottom of a valley? Is it the top of a hill? Or is it a saddle point? And we need to know which of those it is. Or something else entirely. It's almost always one of those if you zoom out far enough. It's almost always one of those. But it could be something really crazy where it's, yeah, I'm just going to call it a saddle point if it's a minimum in one direction and maximum in the other. Yeah, but it turns out that the only test we have for doing this will sometimes not tell you anything. So how do I tell if it's a maximum or a minimum? Because there's only got one, right? If I knew my function was always this shape, then that'd be great. It'll definitely be a maximum. But I have no idea. So I'm actually pretty sure this is a saddle point, just because I know the shape of that one has a saddle point. That's a function I'm very familiar with. I did my PhD on quadrics, and so I know that that's a function that has a saddle point. So I'm guessing that this one probably has a saddle point as well. So that's my guess. So how do we tell? We need the second derivatives for that. So if I would like to know whether it was, let me just step back a bit. If I looked at it from the side, and this is my x-axis and this is my z-axis, and my function was going like this, then that would be a maximum. I'd know that the derivative in the x direction would be 0, but I'd also know that the slope as I go past this point is changing from positive to negative. So if I look at how quickly the slope is changing, it will be a negative rate of change of the slope. So this is the slope positive here, and this is the slope negative here. And so the slope goes from positive to negative. So the rate of change of the slope in the x direction is negative at this spot. And that would be what was happening if it was the top of a hill. And if it was that's a minus VE, by the way. I'm just going to say negative. But if it was a maximum, then it would be going from a negative slope to, minimum, it would be going from a negative slope to a positive slope. And so the rate of change of the slope would be positive. But I would like, if it's going to be a minimum, it has to be a bottom both in the x direction and the y direction simultaneously. And in fact, it has to be a bottom no matter which direction I'm facing. So I sort of need like a directional second derivative, which would be fabulous, but we don't have a definition for that. We have a magic trick. So the magic trick goes that I'm going to figure out the df on dx in both the second derivative with respect to x. I'm going to figure out the second derivative with respect to y. I'm going to figure out the derivative with respect to x and then respect to y, and the derivative with respect to x, respect to y, and then respect to x, and I'm going to find the determinant of that matrix. This is the trick. This matrix here is called the Hessian Matrix. Hessian, I don't know how to pronounce it. This is the Hessian Matrix, and the determinant of that will tell me whether it is a local minimum or a local maximum, or, well, will tell me whether it's a local maximum in or a saddle point. Is there a symbol? I think they use this symbol. No, not that symbol. Ah, the D, let's call it D. D is the discriminant, which is the determinant of this matrix H. And this is what happens if the D comes out as negative, then it's guaranteed to be a saddle point. If the D comes out as positive, then it's going to be one of a maximum or a minimum, but that's not enough information to tell you which one. To decide which one, you're going to have to look to see if this comes out to be negative or positive. Because if the double derivative with respect to x is negative, it'll be a maximum, because it'll be the top of a hill.
Equals, two lines, what does that symbol mean?
This here,
Yeah.
the determinant. Like the literal determinant of the matrix. So this times this minus this times this. So to get a maximum, if this one is positive, then it'll be a minimum. And if either one of those is negative, then it'll be a maximum. Doesn't matter which one. Use whichever one you want. And if the D comes out as 0, then it doesn't tell us anything and we have no idea what's happening there. And we will say, inconclusive, I don't know. And that's a perfectly legitimate answer for your exam if it happens. So let's see what happens for our function. So the df on dx was at y minus 2x, and df on dy was x plus 3. So d squared f on dx squared. That means I do the derivative with respect to x again. The y counts as a constant. I'll get minus 2. So it is totally not going to be a minimum because this is negative. So we've already ruled out this one. It's not a minimum. D squared f on dy squared would be differentiating this with respect to y. Doesn't have any y's, it's a 0. And I have one more to calculate. D squared f on dx dy would be, so if I started with y and then did x, that would give me a 1 in this one. So if I did y dx, I did the other one, I've started with y, do df on dx, and then do d on dy, I would also get 1. And so it works out to the same answer either way. Almost all functions that you can write down a formula for without using crazy stuff is going to work that way. So, okay, and so we got those answers. And so my Hessian matrix, d squared f on dx squared is here, d squared f on dy squared is here, df, they're both 1. And so the determinant of that, sorry? Oh yeah, would be minus 2 times 0 minus 1 times 1, which is negative 1, so it's a saddle point. I'm feeling a need to do an example where it doesn't work out quite so neatly. Yeah. So this function was really special because when I did the second derivative, they all came out to be constants. But it doesn't always work out that way. Sometimes they work out to have other things. But before I move on, I want to just check how people are feeling about what just happened there. What about online? Sweet. Thank you, everyone. Okay, let me do another one to see if I can figure out what's going on. I will say this something very important here. This second derivative thing with the Hessian matrix, it only works if you're at a critical point where the gradient is 0. If you want to know what the curvature is doing at another point, it's a whole other thing. So, yeah. No, yeah, that's not even. It is briefly. I just did the multivariable calculus 2, the second year course revision seminar. It is briefly mentioned in about one line on page 80 of their notes, and they don't even look more deeply into it than that either. So it's just nobody cares. Well, I'm trying to find what the second derivative is doing at a point that isn't a critical point. So we do care about that for one variable functions because it's an easy question to answer, but it's not that easy for for 2 variable functions. Yeah. Just give me a moment. I do not like it, Sem1, so. All right, it's going to turn to utter crap, but I just want to do it. So x times y minus 1 times e to the minus x squared minus y squared. This function is a very bad function, but it's one of my favorites. So, oh, I can't call it y. I shall call it f. Okay. So I'm not covering everything. I'm just talking about derivatives. I haven't talked about tangent planes, I'm sorry, and I'm not going to have time to get through that. But we can do that. You can look at the old seminars for that. Okay. So df on dx is, okay. So let's just investigate what's happening here. I've got an x. That doesn't involve an x, but this has got an x in it too. So I have two pieces that both involve x's. I'm going to have to use the product rule. I'm going to keep this bit and differentiate this bit. And the derivative of e to the power of is the same, but I'll have to multiply by the derivative of that, which is minus 2x, because the y counts as a constant for this story. Oh crap, I haven't finished. It's a product rule, David. So I kept this bit and I differentiate that bit. Now let's differentiate this bit. The constant that's multiplied by the x is y minus 1. And this bit stays the same. I feel like since they've both got this in it, I would like to factorize. And in fact, they've both got a y minus 1 as well. So I'll factorize that out. Because it just feels like a nice thing to do. So I've got minus 2x squared plus 1. Okay. Sweet. It's pretty awful. Should have changed my numbers, but that's okay. Let me do df on dy now. Product rule again, because this bit involves a y and this bit involves a y and they're multiplied together. I'll keep this bit. And I'll do the derivative of this bit. But because of the chain rule, I'll have a minus 2y. And then I'll differentiate this bit. Okay, so this has got an x, a constant x multiplied on. So when you multiply a constant on, it will still be there afterwards. And the derivative of y minus 1 is 1. And then I'll keep this. And they've both got an x, so I'll factorize that out. And then what I've left with is minus, oh crap. Minus 2y squared plus 2y plus 1. Ugh. Oh. Sorry? I brought it on myself. Don't make up examples on the spot, people. This is why they write the exams months ago and get people to check them. Okay. So I need both of these to be 0 at the same time in order to get a critical point. Okay, so let me create those equations. I've got one here. I've got minus 2x squared plus 1 y minus 1. E to the minus x squared minus y squared has to be 0. That's equation number 1. And equation number 2 is, I'm just going to write it down. So when I get my two derivatives and create my two equations, this is what I've got. All right, from equation number 1, I need these three things are multiplied to give 0, so one of them has to be 0. This can't be 0 because e to the power of anything can never be 0. That's impossible. And so I need either minus 2x squared plus 1 to be 0 or y minus 1 to be 0. And so I've got, this would be the same as 2x squared equals 1, which means that x squared would be a half, which means that x would be plus or minus 1 on root 2. And this would be y equals 1. Okay, sweet. Doing well. So, in order for this one to be 0, I need one of those things to happen. There's three things going on there. X is one of these or y is one of these. All right. So I could sub them into the other one and see what happens. Or I could just solve the other one as well. Yeah, just gonna sub, let's just ignore me. Okay, so if x is equal to 1 on root 2, sub into number 2, I've got 1 on root 2. No, ignore me. You have to choose which one you want to do on the day. I'm going to just solve them both separately. Sometimes you have to sub one into the other, and sometimes you can solve them separately. So with this one, I get x equals 0, or minus 2y squared plus 2y plus 1 equals 0. And that looks like a quadratic formula to me. Minus b plus or minus the square root of b squared minus 4 times a times c. No, 4 times a times c over 2a, which is not pretty. Wow, I really did do it to myself. I think if I took the 4 out of there, I'd get a 2 root 3. And then I could cancel some minus 2's. All right, they're my answers. So when x is equal to 1 on root 2 from number 1, the y could be, the y needs to be, if x is equal to 1 on root 2, then in the other equation it's not 0, so the y has to be one of these numbers. Damn it, wrong formula. 1 plus root 3 on 2. And when x is equal to 1 on root 2, we can have y being the other one of those, and that will make the other. So this one makes the first one equal to 0, and this one makes the second one equal to 0. We could have and that's pretty much it for that. But we can also have x being minus 1 on root 2 and y being 1 plus root 3 on 2 and x being minus 1 on root 2 and y being 1 minus root 3 on 2. So that's that. So we did x equals 1 on root 2 and figured out what had to go with that. X is minus 1 on root 2, figure out what went with that. And now the other option is that y is 1. And if y is 1, it can't be equal to this, so the x must be 0. So I get 5 critical points. Yep. Well, you calculate the formula for the Hessian matrix involving x and y and sub all them in. Yeah, that's fine too. So cool, 5 critical points. I shall tell you now, I know in advance because I know this function well, there are 2 local maximums, 2 local minimums, and 1 saddle point. That's the saddle point there, because it's the one in the middle. There is a model of this function in the Maths Learning Centre made out of paper mache. So not this function exactly, but something similar. Okay, so the Hessian, I'm going to need to find all the second derivatives. So I'm going to go back to my derivatives and differentiate them again. It's going to be bad. But it's the same idea. It's going to be partial derivative, sorry, the product rule again. So df on dx minus 2x squared plus 1 y minus 1 e to the minus x squared minus y squared. So d squared f on dx squared would be product rule. I'll keep this. And differentiate this. And then I'll differentiate this, so the y minus 1 will still be there because it's a constant multiplied on. And I'll differentiate this, which will give me minus 4x. And I'll keep that bit. And so I'll end up with whatever I end up with. It's not pretty. I do not like it, Sam I am. It's got a minus 2x in every piece of it too. And so I've got minus 2x squared plus 1 plus minus 2. Oh, that wasn't too bad. All right, there we go. Yep, plus 1 minus 2, which would be minus 1. Yep. Great. And then d squared f on dx dy, I could redo this one with respect to y. Minus 2x squared plus 1, y minus 1, either minus x squared minus y squared times minus 2y. I'm doing with respect to y now. That was the product rule by keeping the first bit and differentiating the second bit. And then this one's got the minus 2x squared plus 1 as a constant multiplied on times the derivative of that, which is 1, and then keep this bit. Right, and that's got a minus 2x squared plus 1 and a minus, and an e to the minus x squared plus y squared minus y squared. And what I've left behind is minus 2y squared plus 2y plus 1. And then df on dy was whatever it was, this. And d squared f on dy squared would be product rule again. And the x will still be there, and I'll differentiate that, which is minus 4y plus 2, which doesn't factorize nearly so neatly as the other one does. And it's not pretty. Good-o. Good-o. So I've got 4y cubed minus 4y squared minus 2y plus, minus another 4y plus 2. Okay. Sweet. And so my Hessian matrix is made out of those things. I have, where are they all? Where'd they go? There it is. I've got this in the top left corner, this in the bottom left, bottom right corner, and this in the other two corners. And so my Hessian matrix, when I do the derivative, the determinant of the Hessian matrix will be this thing in the top left times this thing in the bottom right minus this thing in the bottom left times it again in the top right. Which is the craziest thing you've ever seen. It does have an e to the minus x squared minus y squared all squared in it. So I would now have to sub in one of my points and see what happens, which is what calculators are for. But I can at least, so the d at the point 0, 1, which is one of my critical points, because that was this point here, x is 0, y is 1, is x is 0, so that bit's 0, and x is 0, we get 1 plus y is 1, which is minus 2 plus 2 plus 1 squared, and e to the minus 0 squared minus 1 squared. And so we get minus 1e, sorry? This is squared. Yeah, that's this minus. Because this has got a minus 2 plus 2. So 1 times that, which is a negative number. And so this is a saddle point. Told you. Whereas if I subbed in one of these points, I really must get a good example for this one year. One of these points, it would have come out to be a positive number in the end. And another one, it comes out to be negative. They would have come out to both be positive, and then I would have to go back and check what this comes out to. So let's just check something. If x is 1 on root 2, then this bit comes out to 0, which goes away. And then I'll get 1 on root 2, I'll get a negative number for this, for my final answer. And so it's going to come out to be a local maximum because the second derivative is negative. Yeah. But that's why they don't give you ones of this level of complexity in an exam. One day, I will find the perfect way to write this function so it comes out more neatly than that.
The sort of question that one might ask in the exam is some information we calculate for you?
Yeah.
You have to do it.
Yeah.
Interpret this answer for us.
Yeah, so they probably would have said, you know, d of...
Yeah, d a bunch of points.
So they'll say d of this is equal to this number here. And also, just so you know, d squared f on dy squared at 1 on root 2 is this number here. And this one comes out, this one's positive and this one's negative, and you'll say, oh, well, this is a local maximum. Yeah. So that's what they probably do. And I've seen exam writers write things where you won't know what these numbers are until after you've found where the critical points are, and you go, oh, that's one of the critical points, awesome. And so, yeah, that'll be great. And if you can't use that information, you know you've done something wrong. All right, well, thanks for bearing with me with that. I should have chosen a less horrifying example, but it's almost always true that they choose polynomials because it's hard for them to figure out what the answers are when they're doing the exam if they don't. But either the power ofs, maybe one of less extreme nature than this one, would cause some useful things to happen. All right, thanks for bearing with me. Don't forget, oh, let me stop the recording before I say this.